Hello everyone, welcome back to Kepler. Today we will be discussing the problems for the Codeforces contest round 1079. So let's look at the first problem we have today. First problem is friendly numbers. So for integer x, we can call another integer y friendly if the following condition holds: y minus the sum of the digits of y equal to x. So for example, if we have something like 18, one possible would be 20, where 20 the sum of digits is 2, so 20 minus 2 is 18. So let's look at make some observations on this. Right. It is given that we have to find y minus dy equal to x, and x is fixed, right? Now, before you even think about how we can solve this, first look at this t of y part, the sum of digits. We know that for a current solution, the number is in the range from uh, up to 199, right? 199 to 1. So what is the range for dx? Okay, or dy, whatever. What can be the range for a number in the number which lies in the range 1 to 199? This can be so for example, if I had something like 2 digits, right? If a number is only 2 digits, uh, the maximum sum of digits is for the number 99. Here d of y is 18. Similarly, if I want to check the maximum sum for 3 digits, it will be y equal to 999, for which the sum is 27. In general, for y equal to for less than equal to 199, we have 9 different digits, so 9 nines. So for d of y, maximum d of y is 9 into 9, which is 81. So that means our d of y value can be at most 81. Okay. So this really simplifies the solution. Instead of iterating over all possible y's, which is unreasonable considering the constraints, we can iterate instead over d of y. So for example, check if for d of y equal to uh, or let's call say d of y, right? Suppose I iterate from z equal to 1 dot 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 81. Okay, I check if x plus let's suppose a new number is y equal to x plus z. If d of y is equal to z, this implies that x comma y is a finite pair. Okay. So this is the solution, as simple as that. And so basically for each test case we iterate 81 times, and since we have only I think 500 test cases, this passes very easily, time constants. Okay. Now for the second problem, uh, yeah, so we have a permutation of length n and an array of also length n. To generate a permutation, we call the permutation P generating for the array A. If the array A can be obtained from P by applying some operations of the following type, we choose an index I, perform one of the two replacements. Either we copy P of I to P of I plus 1 or P of I plus 1 to Pi. So to check whether we can go from the permutation P to the array A by either copying the elements from to the adjacent elements. So for example, if we have say like this 1 2 3 and the array is 1 2 2, we can copy 2 to the third position to get the 1 2 2. So this is possible. Similarly, from like 1 3 2 5 4, we can copy this 3 to the right position and the left position to get the final array 3 3 5 4. Okay. So you have to check whether given the permutation P and the array A, whether P is generating for the array A. Okay, so if we take our very simple case, uh, so we have permutation P of n elements, okay, Pn, and even array A of n elements. Now, since this is a permutation, there is only one instance of each number in this, okay. So if A of I equal to x, and suppose P of j equal to x, meaning the x number occurs at the jth position in P, that means that you have to perform the operations in the order j, then j plus 1, then j plus 2, all the way to I, to make the ith element in a x, or ith element in px, or it could be also j to j minus 1, j minus 2, depending on in which order you're doing it. Okay, it's possible as well. Okay. So essentially, we are propagating the jth element to the ith element in a one direction. Now consider an impossible case. A good example is already given here. Uh, mm, oh yeah, this works. So 3 1 2 4 3 4 2 2 3 1 2 4, and the array is 3 4 2 2. Now the second element here is 4. So I have to propagate this from the fourth element. So we copy it from here to here, and then again from here to here. We end up with 3 4 4 4. Now check that the next element is 2. But in the process of copying the fourth element to the second element, we've already destroyed the 2 in this position, right? So we cannot achieve 2 anymore in this position. So that's why this is not possible, okay? So based on this, we can get a very simple observation, which is that uh, suppose for each element, uh, mm, let's make another array B, okay? Array B such that if A of I if A of I is equal to x, then P of Bi is equal to x, which essentially means that uh, P of I stores the index in the permutation which holds the element you're trying to copy. So for example, if we, for example, for in this case, for 3 1 3 4 2 2, our array B will be first element is x, int is 3, and 3 is in the first position in the permutation. So we have 1 here, right? The second element is 4, right? And 4 is in the fourth position in the permutation, so we have 4 here. Then it is third element is 2, okay, and we copy, and the position of third element in the permutation is 3 as well. So 3, and finally for last element is 4. No, last element is 2, and position of 2 in the permutation is 3. So 3 here. Okay. So yeah, just what you notice, we have sort of create a mapping from where we are trying to copy each element. So 3 to 3, 4 to 4, 2 to 2, 2 to 2. Okay. So we have to sort of build a mapping for the elements. So if you notice here, I'll make a claim which is to make an array achievable from a permutation, the B array, B should be non-decreasing. Here there is a conflict and inversion where the B for the second element is more than the third element, so this is not decreasing. So that's why you have a wrong answer here. If you consider the other example, let's say something like this could work 1 3 2 5 4 3 3 5 4. Yeah, 1 3 2 5 4. This is B. A is 3 3 3 5 4, and B would be 2. Take it from here again 2, again 2. I'm taking it this from here. So 2, 4, and 5. This is not decreasing, so it is possible. Okay. Now, why is this such a constraint that if B is not decreasing, then an answer is possible? This is actually very simple to explain. Whenever you have an inversion in the B array, so this means that B of I is greater than B of J for some I less than J. So this essentially means a violation. If there is a violation like this, the problem with this is that this means that you're copying, to bring the ith element to the to make bi possible. We have to go for copy from bi to bi minus 1 to bi minus 2 all the way. You have to copy like this, right? You have to make a series of operations like this. You have to make a bi element possible to same as the I element. But since bj is less than bi, this means that bj must lie somewhere. So j lies somewhere over here, right? J must lie somewhere, let's say in between this. Okay. And let's say bj lies somewhere in here. But since we already moved bi to I, we essentially overwritten these two elements already. So we have lost this data over here, and we cannot copy bj to j anymore because the bj element has been overwritten by bi. So if there's an inversion in the b element in the b array, the answer becomes false. So this simple check is sufficient to check whether the answer is possible or not. Okay. Now for the third problem, problem C. Yeah. So we have two integers p and q. Listen up to a game with two numbers. They can either decrease p by 1 in one move or decrease q by 1. And the game ends when p equal to 0 and q equal to 1. Or Bob wins if the p by q becomes value 2 by 3 at any point. So this is a very quick, very nice question. So it is given that we have some fraction p by q. Can either make this p minus 1 by q. Okay. Or p by q, sorry, p by q minus 1. This is what this means. And Bob wins if at some stage p by q AC becomes 2 by 3. Okay. Now for this problem, it is a very simple solution. First of all, for this array, notice, or this fraction, notice that 2 by 3, the difference between numerator and denominator is t equal to 1, right? 3 minus 2. If you multiply both the numerator and denominator by 2, you get 4 by 6. Here the denominator is 2. Now if we add 2 and 3 to this to the top and bottom again, we get 6 by 9, which is just difference 3. Again, if we add again, we get 8 by 12, the difference 4. So basically, as we keep adding 2 and 3 to the numerator and denominator, we increase the difference between the two elements. Now suppose the given fraction we have has difference equal to q minus p, assumes it's the case. Okay. Now suppose we construct a similar uh, fraction from 2 by 3 as 2 into d by 3 into d. This reduces to 2 by 3, but and also the difference is d between these two elements, numerator, denominator, numerator. Now I'll claim that if p is less than equal to 2 by d, 2 into d, sorry, not less than, greater than equal to, p is greater than equal to 2 into d, and q is greater than equal to 3 into d. In this case, the answer is possible. Bob can achieve 2 by 3, regardless what Alice makes. Okay. Uh, just give me a minute. Yeah, sorry. So as I was saying, um, if we have a condition that is greater than equal to 2 into d, and q is greater than equal to 3 into d, we can achieve 2 by 3 from p by q. I'll prove why this is true because uh, suppose our current array is p by q, right? Plus p by q. Suppose Alice makes this it is a numerator, so it becomes p minus 1 by q. If that is the case, Bob will reduce the denominator, p minus 1, q minus 1. Now the main thing to note here is that since Alice and Bob make reduce two different numbers, here the difference was t, say, and again after two moves, it again becomes t. So the difference remains the same. Similarly, if Alice had made, say, reduce the denominator, q minus 1, Bob could reduce numerator to get p minus 1, q minus 1. If I take an example, say, let's say 4 by 6, let's say, okay. 4 by 6. If Alice reduces numerator, we get 3 by 6. Then Bob makes 3 by 5. Oh, no, sorry, no, okay, this is already 2 by 3, so Alice, so Bob wins regardless. Okay, let's take a different example. Let's say something easy. Okay, let's just say 4 by 5. Okay, if Alice does say 3 by 5, Bob can do 3 by 4. If oh yeah, it's 3 by 4. If Alice does say 4 by 4, let's say, Bob will make this 3 by 4. So you can see the uh, difference remains the same regardless of what they are doing. If Alice, I can see it says here to 3 by 3, Bob can make this 2 by 3. Similarly, if Alice makes it 2 by 4, Bob can make it 2 by 3. So since the difference remains the same in every two elements, every two move, essentially the number will converge onto 2 by 3 regardless of Alice's move. So just calculate the difference between the two numbers p by q, and if this condition holds, p greater than equal to 2 into d and p greater than equal to 3 into d, you can reduce p by q to 2 by 3. Now for the fourth problem. So this is a bit tricky problem. In this array, you're given an array A, and you can call a pair of indices I comma j beautiful if the following condition holds: ai into aj is equal to j minus I. Okay. For example, in this array 1 comma 1 comma 1 1 204, in this array, there are, I think there are three beautiful pairs, like 1 comma 2, because these two elements, the product is 1 and the difference of the indices is 1, so it's true. 1 comma 3 because 1 2 3 because their difference of indices is 2 and the product is 2, so it matches. And finally 1 comma 5 for the same reasons, right? Now I'll propose two different solutions for this. Okay. Um, suppose one is the most obvious solution, which is that let's say we add the ith element. We want to find all j, or let's do the opposite, right? We are at position j, find all I such that I comma j is beautiful. Beautiful. And I is less than j. Now, one simple way to do this is to, since we know that ai into aj is equal to j minus I, this implies that uh, j minus I is divisible by aj, and j is already fixed. So I can be is a multi. I is can be either j minus aj, okay, or j minus 2aj, or j minus 3aj. So basically, we go down in increments of aj. So if you think about the algorithm for a bit, it is something like this. For I equal to uh, ij, we need to j first. So j equal to 1 to n. For I equal to j minus ai, j I is equal to 1, and we decrement I by a of j in each turn, right? And check if I comma j is a valid pair or not. Now, obviously, we can do this in this order of 1, right? This last checking is a simple equation check. This one takes order of n, and this one takes order of n into uh, n into n by ai. That's not I mean, so n by ai. So overall, it's n into n by ai, right? And this is n by ai because it is very simple. Because we are for the jth element, we decrement by aj in each turn. So the number of decrements possible is n by aj. That's why it's n by ai. So obviously, if AI is very large, this will not take too much time. But if uh, AI is like something like 1 or 2, this almost becomes order of n square, right? So obviously, this is too slow. This won't work. So for large elements, for large AIs, we can use this, but for small AIs, we cannot use this. So what can we do about it? So let's say we propose the second algorithm now. The second algorithm, so we know that AI into H is equal to 1 equal to I minus J, right? Or J minus I, whatever. In that case, J can be written as something like J equal to I plus AI into H. Right. J equal to I plus AI into AJ. Suppose what we do is we just simply brute force over all possible values of AJ, right? Let's say we brute force over Y. Let's say Y equal to 1 to, let's say some value mx, okay? Some value m. And let's assume basically we're checking for all pairs for AJ equal to Y, okay? This is what the Y is. So for now we iterate to the array I equal to 1 to n. Now let's say suppose we want to make a pair where I is the first element. So that means second element must be something like J equal to I plus AI into Y, right? Because as I mentioned, I have fixed a second element for the pair AJ as Y, and the first element is AI. So the J index has to be J equal to I plus AI into Y. So if that is the case, mm, so let's make another array count of 1 dot 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 n, which tracks for each J uh, how many pairs, how many I comma J pairs for each J. So basically means that for each J, how many I indices are there less than I less than J, thus that I comma J forms a beautiful pair. So for each I, we calculate the J as like this and increment count of J, implying that uh, basically I comma J forms a pair. Now while iterating also, if let's say we get element where AI is Y, which meaning this can be the valid second element, we add count of I to our answer, okay? Meaning we can accumulate all the pairs we've found so far and add it to our answer. Now, if you think about it, it is sort of like the inverse of the previous problem, previous algorithm. So for the first loop, the complexity gives us something like order of m, and the element for I equal to 1 to n is order of n, obviously. Total complexity is order of n into m, right? M into n. Now we know that m can be at most n itself, because if m is more than n, it is not possible because the maximum value of j minus I is also less than equal to n, right? It's bounded by the number, by the indices of the element of the array. Since j minus I cannot exceed n, the element itself y cannot also exceed n. So m is bound by n. So this becomes order of n square in the worst case. if we go through each possible value of y from 1 to n. So now we have a dilemma like both these algorithms basically reduce to order of n square if we cover all cases with this. But this is where the interesting part comes in. You will see what's happened here is that the first algorithm had a complexity like order of n into n by m, let's say, okay. Let's say, suppose it's, sorry, it was AI here, but suppose it is m, but m is the maximum value of AI we are considering. And second one was order of n into n by order of n into, sorry, n by n into m. Okay. Now we'll do something interesting. What we'll do is to find pairs I comma j with aj more than root n. We use first algorithm, okay. So we use this. So since aj is at least root n, the value of n by m becomes root n as well. So now this becomes order of n root n, right? Because the maximum value of n by m is now n by root n, which is root n itself. And if otherwise, use the second algorithm for elements less than root n. Again, since we in the second algorithm we are going through each possible value of ay or for y ij, of ij. We basically go from y equal to 1 to root n now because we are only checking for aj less than root n. So this essentially now becomes order of n root n. So total complexity now comes out to just order of n root n because we are using these two different algorithms depending on the cases we are checking for. Okay, so to summarize, to find pairs I comma j with aj, where aj is more than root n, use the first algorithm which has a complexity of order of n root n, and for pairs with aj less than root n, we use the second algorithm which has order of n root n time complexity. So total complexity is order of n root n for the entire algorithm. Now I can just show my code a bit because I know it is a bit confusing, so I'll just show my solution. Just C. What's in this PR? No, this is not it. Yeah, yeah. So suppose I set some threshold as 440. 440 is root v5. You can set root and separate as well for each test case. It does not matter. So again, first this is the first algorithm to find pairs. For the first case, I comma j, a of j is less than equal to root n. Okay, this is the first case. So I go through each possible value of aj from 1 to s or root n value, and I use algorithm I showed, but I have a separate array count, and I calculate the jth index from each I and increment like that. And for second case, I calculate all ai aj or I comma j pairs where a of j is greater than root n. Okay. So again, this is the algorithm I showed where I go through each j and then I iterate in the reverse direction in decrements of aj and check if we are aj from the value 2. So I think this is a very cool problem because in hindsight, it might appear that it's not possible because both these approaches reduced order of n square, but by combining them, we have arrived at a pretty cool fast solution for this. So this was problem D. For E, I will go to the hard version directly for E. Now for it is given, it is an interactive problem. So we are given a DAG, reactor cyclic graph, with n vertices and images. You have to find out when you can make a query where we are asked for the ith path in the lexicographically sorted order. Right. So in the ith sorted order, we get the ith path. So for example, if I have this graph, these are the paths in the sorted order. So if I have say query 3, I get this path, or if I query say 6, I get this path. So basically I can make any queries to find out all the edges we have in this graph from these queries. Now this is a very interesting problem. If I consider a very simple case, something like this, 1, 2, 3, 3, 4, 5. Let's consider a path like this, okay, a graph like this. So if we, what I'll do is, for the hard version, we have to make, we can make only order of n plus m queries, okay. So what I'll do is, in each query, I'll try to obtain exactly one new edge which I have not found previously. Now for the first part is simply, first path is simply 1 itself. Second path is 1, comma 2. So what I'll do is, as I'm adding edges, I also build my graph. So this is the graph on my GUD. So let's construct our own graph simultaneously. 1, 2, 3, 4, 5. Suppose we have initially no edges. In the second query, we know that we have found a new edge. So we add 1, comma 2 here. For the third query, it is 1, comma 2, comma 3. So we add a new edge 2, comma 3. And the new edge will always be the last two elements, the path, okay? For a second, it is fourth, so 1, comma 2, comma 3, comma 4. Okay. Then fifth is 1, comma 2, comma 3, comma 4, comma 5. So we add 4, comma 5 edge. Okay. Now I have covered this entire path from 1 to 5. Second will be 1 to 3. Okay. Now we'll add an edge here again, 1 to 3. Now I'll do something interesting. Notice that because the graph is acyclic, there is no back edge in the graph. So that means that if I have a path like this, 1, 2, 3 occurring, the paths occurring immediately after this will also cover all the paths from 3 to other vertices. So what I mean is, after this node, this index, the paths of the from 1, 2, 3, 1, 2, 3, and then all paths from 3. And I can say this is true because for the 3 from vertex 3, we have two different paths, 3, 4 or 3, 5. So these are actually replicated, as you can see, in this next two vertices. So what this means is, we have already found all the edges from vertex 3. So we don't need to actually go to the next element. Instead, what we can do is, we have already queried this, all right. Since you've already found the edges for 3 already, we'll find a number of paths from 3 in the graph you already have. Suppose paths of 3 we want to calculate. Again, to get the number of unique paths from a vertex in a THG, it is a very simple recursion problem or a DP problem. We can solve it on your own, but essentially the number of paths here is 1 here, for 1 for 5, 1 for 4, and 2, 1 for 5, 2 for 4, because 4 and 4, 5, and only 3 for 3, because 3, 3, 4, and 3, 5. Okay. So number of paths for vertex 3 is 3. So now instead of incrementing by 1, we increment directly by 3. So what this, if you look at the next 3 paths we had here, plus 1, 3, 1, 3, 4, and 1, 3, 5. So we ignored this 7, 8, and 6 plus 3, we jump to 9 directly. So now we get now we get the next part 2. Okay. So what we've done is we sort of skipped a few redundant parts by using the edges we already found in the graph. Now for the next path here, we have 2, 3, right? Again, we know that we have already found. Well, actually, we don't need this as well because for 2 also it is already calculated, right? For 2, we already know the paths, so we can skip from 2 as well. So for 2, the number of paths is 4, 2, 2, 3, 2, 4, 2, 3, 4, 2, 3, 4. So if we look at the thing, 10 is 2, 3, 11 is 2, 4. Sorry, not 2, 4, 2, 3, 4. 12 is 2, 3, 4, 5. We skip this entire thing, okay? We skip this all and we directly go to 13, which is 3. And we can repeat the same process. Again, for 3, we already know the it is for from the node 3. So we use this path of 3 is 3. So we go to 16 directly, which is 4. Again, we know for 4, it is already known number of paths. So we go to 18 next. We go to 5. And we go to 19, which is empty. Because there are only 18 paths in this graph, okay? So we is the answer for this. Now if you look at the number of queries we made, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Number of edges we have is n is 5. And m is 1, 2, 3, 4, 5, 6. Yeah. We have successfully found the entire graph in just 6 queries. Okay, I think I made a mistake here. I missed the 1,5, but you can find that in the same process as well. Okay. So basically, whenever you find a repeating vertex in a query path, use the number of paths you've already found from the vertex to skip a few queries and jump to the next possible query. So this solves the problem in order of n plus n time. Okay. Order of n plus n queries. There is also another solution for this. For E1, you could make 32 into n plus m queries. So for the first easy variant, you could also do something with binary search. So instead of using DP to find the number of paths in a vertex, you use binary search to find the next viable ID or viable index, which gives us a new edge. So that is with 32 into n plus m. But you can try solving that on your own. That is a good practice for you. But yeah, the idea remains the same, where you try to skip a few queries to get the next query with the new edge. Okay, so that is for problem E. Now for if, okay, let me just show the solution for E as well. It will be easier for you guys. See, yeah. So like as I mentioned, I start from the second. You can start from the second query, because you know first query will be 1, so you can skip that as well. So start from the second query, and I get the path for this ID, and if this path of length of the path is less than 2, only a single vertex, you can skip that. Otherwise, you add the last 2 elements as the new edge, and again, if you see that the number of edges for the last element is not empty, meaning we have already found the edges for the last element, you can do a DFS, or you can use a DP to find out number of paths from this last element and skip uh, a few queries or skip a few indices using this number of paths. So let's look at the last problem now. Bracket sequence. Yeah. So I won't take too much time over this. You can try this on your own. I'll just give you a brief idea how you do this. Essentially, we have a sequence of characters with 2 types of brackets, round and square bracket, right? And you can change each character into any other character. You have to find out the minimum number of moves you have to make, so that the sequence of all round brackets from a bracket sequence, kind bracket sequence, and sequence of square brackets from a correct bracket sequence, right? So to find the number of operations to make the entire string valid. Now, if you consider different combinations of pairs, for example, if you consider the number of pairs which are already valid, meaning we require here moves to correct these pairs, it is these two, right? Now, if you think about the pairs which will take at least one change to correct them, it can be something like this, with 2 close or 2 open, or even something like this, or this. There are a few more like this. Now, there can also be a case where we require 2 operations to correct a pair, and these are basically this, I think. Yeah, like this, 2 mismatch pairs, and also opposite direction, also like this. Okay, so this will take 2 operations to correct, because you have to flip both these two in order to fix it. And this will also be taking 2 operations, right? Yeah, this will also take 2 operations. So anything of this form will take 2 operations to correct if we have 2 different directions for the brackets. Suppose we find the longest parenthesis sequence, which is simply longest valid sequence of brackets. For example, if we consider something like this, in this case, the longest valid sequence for square brackets is something like this, 2 open, 2 close, and for round brackets it is open, close, close, right? So let's say we sort of pick off the elements which correspond to this longest sequence. Suppose we pick off these 4 for the round sequence, and these 4 for the bracket sequence. So we're left with if we remove these two valid sequences, we'll left with something like this. Close, close. Okay. So this will take 2 operations to fix. So the answer is actually 2. And we're doing this because if we consider what we're doing with this example, and we find the longest valid sequence for each type of bracket, essentially for all this all for the sequence, we get multiple pairs which require uh, 0 operations, right? Like I mentioned here, if we have 2 matching brackets like this, we get 0 operations to fix them. They already in the correct order, so we get a set of pairs with 0 operations. And same for this. So after this, we are left with whatever string we are left with after removing the sequence. It has no pairs which can have any matching any 0 operation pair. It will require either 1 or 2 operations to fix them. Okay. So now once you have removed these 2 sequences, our problem becomes deciding whether the remaining pairs can be fixed with 1 or 2 operations. Now other thing to notice is that we can only have at most 1 2 operation pair. Why? Because suppose we have we claim that we have 2 different 2 operation pairs. So like I said that 2 operation pairs are of the form like this in the opposite order, both the brackets. Something like let's say the first pair is something like this, right? And second pair is something like this. We can just pair up these two instead. So pair up these two. This is one operation, and this 2 is 2 operation. So essentially, we've removed one 2 operation pair and converted to 1 operation pair. So this means that if we have 2 different 2 operation pairs, we can just rearrange them to convert remove one of them and get only 1 2 operation pair. So if we have a sequence remaining with no valid pairs, it can have only at most 1 2 operation pairs. So what is the condition for 2 operation pair, right? This is the only thing we need to find out. So this is quite easy actually, if you think about it. Since I mentioned already, for 2 operation pair, the brackets must be flipped in the reverse direction. So this occurs only when I have a sequence something like this. First I have the closing brackets, then I have some opening brackets, and this is a such odd length. Okay. So the reason why this happens is, in order to make a 1 operation pair, you have to make sure that the 2 brackets are not facing in the opposite directions. So you can pair up either 2 closing brackets or 2 opening brackets to fix this. But since we have both these are of odd length, we are forced to pair up a closing bracket and then opening bracket together. Just operation has just a cost of length of 2. So if after removing the 2 valid parenthesis sequences from the string, we end up with a string like this where we have odd length open first, then odd length close, or sorry, odd length closed and odd length open. In that case, our answer is 1 2 operation pairs plus 1 operation pair. So essentially, in general, if you have a string of length m, number of operations is m by 2, because in each move we pair up two brackets and fix them, plus 1 if there exists some two operation pair. Okay, like I mentioned here, this sequence has a two operation pair, so you add 1 for this case. So this is the solution. So you can calculate the longest parenthesis sequence using a Monotonic stack or some other approach. It's very simple. You can do it on your own. Mark these brackets in the sequence and then remove them from the original string. And you get the new string from here, which has no good pairs. Then check if it is a condition where it has two operation pair, and based on this, find the number of operations you need. Okay, so that's all for today. I hope you liked the explanation for my problems, and if you liked it, please make sure to like and comment on this video. Also make sure to check out the website for Kepler. You can find the notes for the video over there, as well as other resources. So that's all for today. Goodbye.